Thanks for the introduction. I apologize and I regret that I cannot be there in person, but hopefully this is still as fruitful for everybody. I'm still very excited to show you some of our recent results. So today I'll be discussing how we can manipulate different kinds of magnetic excitations in oxide materials. And this is really a team effort. So what you're looking at here, the work you'll be seeing is from a variety of different places. These are the people that actually did the work. You'll see some work from my time at MIT, my time at Berkeley, in collaboration with groups and industry across the world. Currently, I'm an assistant professor. I just started a group at Brown University. So the data you'll see is from both my postdoc and my PhD. And so what do I actually mean by magnetic excitations? Well, as was very nicely introduced already in this session, I'm discussing things like non-collinear textures, such as domain walls, which can be chiral in some cases, things like two-dimensional bubbles or topological systems like skyrmions, even more elementary excitations, things like magnons or spin waves. And what you'll find is what we're very interested in and what excites us is really the ability to manipulate or stimulate these kinds of excitations to control their propagation and to control their dynamics. And so what I'll show you today is work where we can manipulate these different types of excitations, particularly in oxide materials. And the reason we're interested in oxide materials is because we can exploit some novel functionalities that these materials have. So things like correlated phenomena, non-trivial band structures, and really importantly, the ability to control these materials very, very precisely using atomically precise growth techniques. So this will allow us to uncover some new physics, a lot of which I'll talk about today, things like chirality, ultrafast dynamics, and the effects of interfaces in these systems. And what you'll see is we basically have a two-pronged approach for attacking this materials physics and this science. And that's by using advanced growth techniques. So you'll see materials grown by pulse laser deposition and off-axis sputtering, as well as combining that with in situ characterization techniques. So what you see today is a lot of in situ imaging techniques and electronic measurement techniques. So with that, here's the outline for the talk today. I'll try to get away with telling you two different stories about two different oxide materials. One of them is a garnet oxide material, a historically widely used system that was already introduced earlier in the session. And I'll also talk about a perovskite oxide system, which is a correlated system. And through these two materials, I'll show you how we can actually excite dynamics so fast that we see relativistic effects, as well as the ability to control magnon propagation just by using electric fields. And of course, this underlying theme of using both synthesis and in situ characterization to access this physics will be highlighted throughout. So I'll first start off with this first story about garnet oxides. I don't think I need to motivate this very much, so I'll go pretty quickly. The previous presenters did this quite well. But as a reminder, most data on Earth is actually stored magnetically using magnetic materials, either through magnetic tape, which is a still hot area of research, as well as hard disk drives. So if you look at something like an IBM data center, such as the cloud here, you'll find that the majority of the data is actually stored on hard disk drives, where if you zoom in on platters or disks, you'll find billions, if not trillions, of magnetic grains or bits, where the magnetization state of one or a group of these bits constitutes a 1 or 0 bit of information. Now, this has been the predominant storage method for quite a long time. In fact, it's really withstood the test of time for a number of reasons, but mainly because it's very inexpensive to make these materials, and you can get very, very dense memories and data storage out of it. So these bits are on the order of 10 nanometers in size or so. However, what's perhaps obvious is the inherent limitations of this technology, such as the inherently slow write times. Because this device is mechanical, it's also not very robust. So the field, as has been explained already, has been shifting towards going from something where you have a hard disk drive, where you have physical, discrete bits that physically move the system, to something more solid state, where you have a continuous magnetic media, where you have different regions, or what we call domains, of uniform magnetization separated by finite regions or transition regions between these domains called domain walls. or these are non-collinear textures. And so if you can stimulate or drive these non-collinear textures into motion, you can effectively move bits back around. This has also been conceptualized not just in using 1D non-collinear textures, but actually 2D non-collinear textures as well, using things like bubbles and skyrmions. So this kind of begs the question, so how do you actually manipulate these magnetic textures? Well, the most popular way to do so today is using spin-orbit torques. And I'll just remind you, this is a way where in heavy metals, 5D transition metal oxides, topological insulators, and other large spin-orbit coupled systems, and even some magnetic materials, you can pass a charge current in these materials, and the spins of the different charges actually get separated or sorted depending on their orientation. And so effectively, you can take a charge current and turn it into a transverse spin current, which has angular momentum. This is more easily seen by the cross-section here. And so this is a more efficient process than using something like a spin transfer torque. So essentially, if you place one of these materials, these spin-to-charge converters, next to a magnetic system, you can actually take this charge current and drive a torque into the magnetic material. And the beauty of this is not only its efficiency, but you can actually apply this sort of spin-orbit torque to a larger array of materials. So things like magnetic insulators, which we'll look at today, and antiferromagnets, which we'll also look at in today's talk. And this has been demonstrated. We've known this, of course, for over a decade. It's been used to both drive domain walls and switch the magnetization of different types of magnetic materials. So the canonical system that's used predominantly today to study domain wall dynamics is an all-metallic system. It's based essentially on elemental magnetic systems, where you essentially have a thin bilayer of platinum or some other heavy metal coupled to a ferromagnet that's once again usually elemental in nature. And so this structure is actually quite useful. It gives rise to many effects such as PMA, which is needed for scalability, and also stabilizes the correct type of domain wall that's needed to drive motion in domain wall. It stabilizes an AL type from the Dzyaushinsky-Maria interaction. And this is important because these types of spin-orbit torques, these traditional spin-orbit torques for materials like platinum, really only act on domain walls with some Néel character. So the strength of the torque is a function of the domain wall angle. And so this device works pretty well. These material systems work okay. So here I'm plotting the domain wall velocity as a function of current density we're applying through the spin-orbit torque creating layer. What you'll find is that you can achieve domain wall velocities that are on order of a few hundred meters per second, which seems reasonably fast. But if you take a closer look, what you'll find is if you model this data, you'll see that there's a linear regime where the domain wall responds linearly to the current. This kind of makes sense. The more current you pass through the platinum, spins that are generated, and torque that's exerted. But there's also a plateau regime which actually limits the domain wall velocity. This is fundamental to ferromagnetic materials. And it's really this plateau or the saturation effect that's kind of limited the propagation speeds of domain walls for a number of years. So where does this plateau actually come from? It actually comes from the domain wall structure itself, or what the magnetization looks like within the domain wall. In fact, when you drive a domain wall with a spin-orbit torque, not only do you drive it into motion, but you also distort that domain wall towards a block configuration, essentially away from the Néel configuration, which absorbs the torque. So it's not the static structure of the domain wall that's important. It's actually the dynamic structure of the domain wall that's causing this plateau. So luckily, a few years ago, our group, as well as a few others, discovered that just by changing the magnetic material system you're using to something that's more compensated, like a ferromagnet with multiple magnetic sublattices, you can overcome this. So one common example is to use a rare earth transition metal alloy, where you can easily control things like net magnetization and the net angular momentum of the system by tuning things like temperature and composition. So what it turns out is these equations of motion, or this model, actually fundamentally changes when you use these types of materials. You can account for the net magnetization and the net angular momentum in these expressions up above, ferromagnet, and adapt them. What you find is what's actually important is the angular momentum. If you have a system that's completely compensated, meaning that it has no net spin, what you'll find is that the equations of motion for this domain wall are change quite dramatically. So instead of having a linear regime and a saturation regime, in fact, you just have a linear regime. The velocity is always proportional to the current. You always get linear dynamics. And in fact, we proved this. So using a completely compensated gadolinium cobalt system, we've achieved purely linear dynamics. Not only that, we've actually even reduced the critical current densities required for motion and even increased the mobility of the domain walls with the slope of this curve. And this is really enabled by in situ measurements, interoperando Kerr effect measurements, as seen on the right. And this is not only seen by our group, but it's been seen by many other groups and confirmed a few more times. So this is quite a known phenomenon at this point. So really what's left to engineer are things like the domain wall mobility or the slope of this curve. And what dictates the slope of this curve, if we go back to the equations of motion, is a few materials parameters. There's the gyromagnetic ratio and the domain wall width, which are actually pretty hard to engineer, or they scale in the wrong direction. So for example, the larger the domain wall width, the larger the mobility, which is not scaling correctly. However, in the denominator of this equation, we have the Gilbert damping, which is actually quite easy to engineer depending on the type of material you have. And in fact, metallic systems, such as all the ones I've shown so far, are actually, the mobility is actually limited by the very large damping because of conduction electrons. However, there's a system that's quite more famous, garnet systems, which have already been introduced in this session, which are famous for not only their low damping, but also their tunable damping. And so what I'll show you is by engineering garnet hybrid metal oxide heterostructures correctly, not only can we drive domain wall dynamics much faster with higher mobilities, but this plateau that you actually see in domain wall velocity is not the same plateau that you saw for ferromagnets, but in fact, it's a fundamental limit, the relativistic limit of how fast the domain wall can move. And so let me first describe a little bit about these types of garnet materials, more about their structure and their magnetic structure as well. They're very complex oxides. They have very large cells with ions sitting in many different sites. But magnetically speaking, they're actually quite simple. They consist of just 3 magnetic sublattices, an iron tetrahedral sublattice, which is antiferromagnetic coupled to the rare earth dodecahedral site, if you choose to use a rare earth, and of course the other iron sublattice as well. And the interaction between the octahedral site and the dodecahedral site is quite weak, so we typically neglect this. Now the beauty of these systems is just by choosing this rare earth ion, you can tune a number of different materials parameters, such as the anisotropy. You can even control the dissipation in these materials, and of course their magnetization and angular momentum as a function of temperature. And here up above, I'm just plotting an example of that, the magnetization as a function of temperature for a variety of different rare earth iron garnets. We can control the compensation, all while retaining very high Curie temperatures in these material systems. So these systems have been around for decades, even in thin film form. They've been around, I think, since at least the 60s, so that's over 50 years. So why is it that we're interested in them now? Well, really, one of the main reasons that we're interested is because we can grow them very high quality with very thin thicknesses. And by thin, I mean just 1 or 2 unit cells while retaining a lot of the bulk properties, like the bulk magnetization. And so this allows us to really use interface effects to drive or dictate magnetic properties. So for example, we can use magnetostriction from lattice mismatch with substrates using epitaxy to induce perpendicular magnetization in these materials. You can also use torques that are driven across these interfaces to induce magnetic switching, which has been shown earlier in this talk, in this session as well, using just currents. And more recently, our group, as well as others, which was described earlier, has discovered things like chiral nail domain walls and chiral exchange interactions across various interfaces in these material systems as well. So this, combined with the damping and the other tunable properties, really give us all the ingredients that we need for ultra-fast dynamics in these material systems. So what actually fundamentally limits the velocity of a domain wall? Well, this is actually a solved problem, solved almost 50 years ago in the 70s by a few different groups. I just named a couple papers here, but it turns out that solitonic quasi-particles, such as domain walls, can really mimic relativistic kinematics. And one way to think about this is a solitary, solitons or solitary wave packets are essentially a superposition of spin waves. So what limits the velocity of domain wall is really what limits the spin wave group velocity. So in other words, maximum velocity of the domain wall is the spin wave velocity. And this was proven algebraically and analytically by a number of groups in the 70s and 80s. And even more recently, this effect has actually been shown as well using things like computation. So atomistic simulations and other types of simulations have shown that this limit does indeed exist, and they even propose material systems to access this limit, particularly compensated systems. So we chose to investigate this using a specific kind of magnetic insulator, a bismuth-doped YIG sample, bismuth substituted, excuse me. And the advantage of this system is, once again, it's somewhat compensated, so we get fast dynamics. And it has much lower damping even than other rare earth iron garnets. It's about a factor of 10 to 100, sometimes even more lower than other rare earth iron garnets. The challenge with this material system is that it's actually pretty difficult to stabilize the DMI in this material. We've had pretty bad luck to stabilize nail-type domain walls. So the domain walls are actually intrinsically immobile. They're the wrong type. They're block, not nail. However, we can get around this kind of cheating in some ways by applying a small in-plane field to the sample to reorient this block domain wall to a nail configuration. This field is larger than the domain wall anisotropy, but much lower than bulk anisotropy of the film, the PMA. And so this is exactly what we did. We can nucleate domain walls and racetracks, apply fields to stabilize nail domain walls, and currents to drive these domain walls into motion. And what you find, again, on the left here is a plot of velocity as a function of current density. And you'll see that these domain walls follow a similar 1D model. Oops, excuse me. We have a linear regime, saturation regime, where now the saturation does not depend on the strength of the DMI. It actually depends on the strength of the in-plane field you apply. So the larger the in-plane field, the stiffer this domain wall, the more it resists its deformation towards a block configuration. And this is proven experimentally. So the larger the in-plane field that you apply, which is shown here on the legend, the higher this plateau velocity. And what you might notice is the y-axis of this plot is actually quite high right now. So we're in the thousands of meters per second with these domain walls. And in fact, on the right here, I've plotted what the saturation velocity is, or what this plateau is, as a function of the in-plane field. You see it's indeed quite limited. What's interesting, though, is if we keep increasing this in-plane field, what you'll find is that these curves begin to stack up on one another. And in fact, this saturation or this plateau itself does not get any higher. The plateau itself plateaus, you can see on the right. And so what we find is that this actually can't be explained, or couldn't be explained, by any existing model of domain dynamics, but could quite easily be explained by the Lorentz contraction of the domain. So this velocity is actually independent of the restoring torque. So no matter how stiff we make the domain wall, no matter how hard we drive the domain wall won't go any faster. And so one can actually calculate the dispersion relationship for this material system. So there's no fitting parameters here. These are all experimentally measured parameters. And what you can find is if you take the derivative of this, you'll get the group spin wave velocity. That's around 5,000 meters per second, which is quite close to what we see. So within 10% of what we see experimentally. Which means that essentially we have to take into account the Lorentz contraction of the domain wall as it's traveling this fast. And so we can analytically and numerically compute what this domain wall Lorentz contraction would be as a function of speed, and even experimentally infer what the Lorentz contraction of the domain wall is from this data, find that these match quite closely. So we've adapted the ferromagnetic domain wall motion equations that I showed you earlier, this 1D model, to account for this Lorentz domain wall contraction. And we can do this analytically with these equations, and also using numerical simulations. And what we find is that these models, both qualitatively and quantitatively, match the experimental data quite well. And so essentially we can access relativistic physics using tabletop experiments. This is all done at room temperature. So this has some practical implications. So it actually tells us what the fundamental limit of how fast these domain wall devices can operate. It also gives us kind of a new playground to study new types of physics as well. I'll just briefly mention before I move on that it's these same compensated magnetic systems that have given us fast domain world dynamics, but also give us very small spin textures. So we've stabilized some of the world's smallest room temperature skyrmions in these material systems, as small as 10 nanometers in diameter. We can even drive dynamics in these systems, not by using currents or fields, but just by using light. So this work is still ongoing. And we can drive domain worlds in skyrmions just by using ultra-fast light pulses. And this is all, once again, enabled by imaging techniques, either in the lab setting or at a synchrotron, both access this materials physics and apply it in. And so that takes me to the second part of the talk, which I'll go through a little bit quicker because I'm short on time, but it's brand new, hot off the press, where we use perovskites, correlated systems really to control magnon propagation in materials. So one advantage of using spin waves as information carriers is that they can transmit angular momentum over actually a much longer range than spin currents can. So on the order of centimeters rather than just hundreds of nanometers without dissipating. The most touted reason for why people like to use things like spin waves is that magnons don't involve any motion of electrons, and so propagation of magnons involves no Joule heating, which typically means pretty low power dissipations. I think these systems are quite interesting because of the logic and memory operations you can perform. So not only just simple Boolean computing, but also nonlinear computing and even wave-based computing, where you use the functional properties of the wave itself. And in fact, these sorts of technologies are scalable. The smaller you make these devices, the better they perform. I'll just note in particular with antiferromagnetics, we have other additional factors that are advantageous as well, such as higher bandwidths, more robustness against magnetic fields. And from a physics standpoint, you can actually have both left and right-handed polarizations of magnons in antiferromagnets. And so there's been a number of different ways that the community has both created and detected spin waves, both in incoherent and coherent ways, such as using optical techniques or spin pumping and their complementary detection mechanisms, but also incoherent techniques such as using spin Seebeck effect and the inverse spin Hall effect or the spin Hall effect to generate spin waves. So in today's talk, we'll mainly be talking about thermal generation via the spin Seebeck effect and detection, incoherent detection using the inverse spin Hall effect. And so a popular way that these are exploited, particularly once again in garnet materials because of their low damping, is by using what's called a non-local spin transport geometry, whereby on the surface of one of these films, you pattern electrodes that are typically metallic, in this case using platinum. It's both a spin source and a spin drain or spin sink. And I mentioned various excitation mechanisms of spin waves. Using this sort of geometry, you can excite spin waves in two different ways. One by using the spin Hall effect, or what they call a spin flip scattering mechanism. It's angular momentum that gets accumulated at the interface, can cause spin wave generation. But you can also just use Joule heating, the spin Seebeck effect, to create a thermal gradient and thus create magnon propagation as well. And inevitably, both of these happen at the same time, but luckily there are ways that we can actually disentangle the effects of both the electronic and the heat-induced mechanisms. So not only has this been seen in ferromagnets, but also antiferromagnets as well. The common material is hematite, or Fe2O3, and this has been observed both in its easy axis and its plane magnetic configurations. What I'll highlight here is that the main mechanisms of manipulating spin waves from one electrode to the other have mainly been using applied magnetic fields. So all these plots and diagrams use magnetic fields to control how much of the spin wave gets to the detector. There have been a few studies which have used three-terminal type devices, such as this one here. There are a few others as well that use magnonic crystals or magnon scattering to kind of control the propagation of magnons from one terminal to the other, creating some sort of transistor. But in fact, I think there's a lot of opportunities to manipulate spin waves. More importantly, take advantage of the functional properties of spin waves, such as their phase and their amplitude. So the question that we've raised is, can we use another stimuli to manipulate magnon propagation, and in particular use electric fields? And the answer is yes, and so the way we're going to do this is by using bismuth ferrite. Bismuth ferrite is a correlated perovskite oxide. It's both an antiferromagnet and a ferroelectric, where both of these order parameters are coupled. So this is the only single-phase room temperature magnetoelectric material that we know of. So the ferroelectric polarization actually points along the 111 direction, or the pseudo-cubic diagonal, and it's a G-type antiferromagnet. So in fact, hematite is actually the parent compound of BFO. So they have very similar sort of magnetic structures. So it's G-type antiferromagnet, and it does also have a small canted moment, which arises from the DMI on the order of 6 EMUs per cc. However, this material is not hexagonal like hematite is. It's actually rhombohedral, which is also a derivative of hexagonal, form of a hexagonal crystal structure. And this mainly comes from the polar displacement that you see from the polarization, as well as very strong oxygen octahedral tilts in these systems as well. But the key thing to keep in mind, the most important thing that you should remember about bismuth ferrite is that the polarization, ferroelectricity, the Néel vector, and the small canted moment are all orthogonal. So if you get lost, it's just a right-hand rule between all three of them. The other thing to keep in mind is that these three are all coupled. So if I reorient one of them, I also reorient the other two. This has been demonstrated a few times, but if I switch the polarization with an electric field, I also switch the Néel vector and the canted moment vector as well. So you can get deterministic switching of magnetism in this material. And so can we use bismuth ferrite to manipulate spin transport using electric fields? Well, this is actually a question that's been brought up for over a decade. So Joel Moore and Souza both predicted that this would be the case in bismuth ferrite, and even over a decade ago, there's been some work on manipulating spin wave frequency in bismuth ferrite using electric fields. But here we're more interested in actually using electric fields to control propagation. And so how we do this is we grow this material in thin film form. The challenge with bismuth ferrite is that in its bulk phase, all orientations of the polarization along each cubic diagonal direction are degenerate. So these are all equal likely to form, which means that the magnetic orientation also has 8 degenerate orientations as well. Luckily, we can use epitaxy or atomically precise synthesis and use strain from symmetry-breaking substrates like orthorhombic substrates to just isolate 2 of these vectors. So instead of having all 8, we can actually stabilize just 2, which are along kind of across a base diagonal that you can see here. So if you look carefully, the out-of-plane polarization cancels out, but there is a net in-plane polarization. And I'll spare you the details, but we can actually measure this net in-plane polarization using techniques like piezo force response microscopy, which is shown here. And this is actually exactly what the structure looks like that we've designed in between 2 of these non-local electrode devices using platinum as our electrode contact. And so the beauty of this net polarization is that we can actually latch onto this net polarization and use it to control magnetism of bismuth ferrite in the exact same geometry. So by applying electric fields across these platinum electrodes, we can actually oscillate the polarization back and forth in this material with non-volatility, which also means we control the magnetism. So we can do this all while doing this non-local measurement. We create magnons thermally and measure them electrically. And so there's a process that we use to do this. We can essentially polarize the material, measure the non-local voltage, and do some checks to make sure that we haven't switched the polarization state after we've measured the non-local voltage. And what you find is that when we do this, here you're seeing a measurement, an experiment where we measure the non-local voltage as a function of time. We oscillate the electric field every 100 seconds. You can clearly see that we see 2 different distributions depending on the voltage applied that actually change sign. So we can change the sign of the non-local voltage just by applying an electric field. So why is this actually happening? Well, I can explain this very simply by using this right-hand rule that we know about in bismuth ferrite. So it's quite complicated, so I'll walk you through this arrow by arrow. So as you can see in this configuration, polarization, red arrows have a net polarization to the left. And of course, I've explained that if you apply an electric field, you can orient the polarization in the opposite direction. This also comes with reorientation of the Néel vector and the magnetization as well. And if you look closely, you'll see that, skip a few things here, you'll see that as we switch the polarization, the magnetic orientation or the canted moment goes from right to left to right. So this is more easily seen if I just take a look at the cross section. What you'll find is that the polarization goes from right to left in one case, and the magnetization canted moment follows that. As we switch the polarization, the same thing, what you'll see is the polarization goes now from left to right, and the canted moment also goes from left to right. Thus, because the canted moment is switching, the types of spin waves, the spin polarization of the spin waves that transfer the material are opposite, and thus you get different signals across the platinum electrode. So by controlling the polarization and thus the canted moment, we can control the sign of the anomaly. In fact, we can do a hysteresis measurement where we measure the hysteretic response of the non-local voltage with an electric field, and we find that that the coercivity here of this hysteresis closely matches with the polarization hysteresis loop. So indeed, the non-local voltage is switching with a polarization switch. We can do some control measurements, for example, on YIG, which is not a ferroelectric, so we don't expect any sort of ferroelectric hysteresis, and thus we don't see any non-local voltage change. So we know it's not any circuitry of the system that's causing it. We can also do this on a ferroelectric, which is not magnetic, which has, of course, a ferroelectric hysteresis loop, but has no non-local change as well. So this proves that it's not a dielectric effect enhanced from the ferroelectricity that's also causing this. So I think I'm over time. So what I'll do is I'll summarize really quickly. I hope I've shown you that by using atomically precise synthesis, combined with some unique ways of image materials, that we can understand some of the physics, both in controlling domain wall propagation as well as magnon propagation in oxide material systems, and look at new physics, exploit new functionalities. So with that, I'll end here. I'll thank once again all the collaborators at MIT, Berkeley, and across the world. And I'll finally highlight that I also just started a group at Brown, and we are hiring at all levels. So if you're interested in using atomically precise materials to look at spintronics or other quantum effects, feel free to shoot me an email. So with that, I'll thank you for your attention, and I'm happy to answer any questions.
Thank you very much. So, are there any questions?
Thanks for the very nice talk. I have a question on the relativistic motion of domain walls in bismuth-substituted yttrium iron garnet. So you plot experimental contraction of the domain wall width. So how do you measure this?
Yeah, good question. See if I can find it for you. Back up. Should be. So we don't measure it directly. So we measure it essentially. If you look, you essentially normalize what the maximum velocity that you're currently at is to some control, some velocity at low in field where you see the saturation. So by using that, if you look at the paper, it's more directly in the paper. But if you do this sort of ratio, a lot of things cancel out. Estimate a normalized domain wall width just from this data that you see on the screen. So we're not measuring directly, we're just inferring it from the experiment. And so it's basically a sanity check to make sure that contraction that we're seeing agrees, or that we're inferring agrees with what we're seeing from the model. So this sort of saturation of the saturation isn't in fact coming from some other effect. It's in fact from the source. It's more of a sanity check thing. Yeah.
Okay. And in the measurements of the magnon in the bismuth ferrite, so you measure also the first harmonic. So you say that you thermally excite the magnons, but do you see anything in the first harmonic measurements?
Yeah, good question. I don't think I need a slide for this, but so yeah, we measured the second harmonic in the experiments that I showed. If we measure the first harmonic, we don't see anything. And the reason we don't see anything has to do with the domain structure. So if you look at what it looks like between the two electrodes, these domains are actually oriented parallel to the electrodes. And these domains of the different polarization of bismuth ferrite are actually elastic in nature. So there's a structural change across each of these ferroelectric boundaries. And we expect that this is causing a lot of magnon scattering, essentially. And so you don't see any first harmonic. What I will tell you is that there are students working on what's called single phase BFO, single domain BFO, where you don't have any domain walls, and they do indeed see a first harmonic. So you can get the electronic effect if you're able to engineer kind of these 8 degenerate polarizations of bismuth ferrite correctly.
Okay, thank you.
Yep.
So if there are no more questions, I think we should really move on because we are quite late. So thanks a lot.